Hello everyone. Today we have section 4.4, tangent planes and linear approximation. So this is similar concept with Calculus 1. So tangent plane, in Calculus 1 we talked, and previously we talked about tangent line, right? So we know that what is tangent line. The line is just touch the graph, right? Okay. Then calculus 3, what is the tangent plane? So we have so many tangent line, right? So slope of tangent line, we learned. That's why with the partial derivative in the previous section, right? So we have a surface, we have so many tangent lines, so we called that is a tangent plane, all right? Okay, so we might think the plane touches the surface, right? Okay, so here is many tangent planes. So we called this a tangent plane at the point, right? I mean the so many tangent lines at the point. So we called tangent plane. This is a tangent plane. So we might think touch this surface, right? Okay. Now then we have an equation of tangent plane. We denote S as surface at the point. Okay. Now, so this is a general point, but we have only X naught and Y naught, right? Okay. I will not prove how to get this equation. I can just insert the proof, or you can read if you are curious about this equation, all right? Okay, so here is 2 pages about the equations. Okay, so let us do example apply with this equation, okay? So we have to find the equation of the tangent plane to the surface by the function, all right? So we have a point which is x naught, y naught. And then let's bring this equation. My handwriting is too big. Copy, paste. Okay, so let's make partial derivative with respect to x here, and then partial derivative with respect to y, and then we do evaluation when x not equal to 2, y not equal to -1. Okay, so let's do that. So partial derivative with respect to x. So first term, we got 4x. Second term, treat y as constant. So we have a -3y, right? And then we have a third term, it's 0 because y is constant. And derivative with respect to x, we get 2. And then derivative with respect to x, 0, 0, right? So we have 0, 0. Okay. Let's evaluate when x naught equal to 2 and y naught equal to -1. So f partial derivative with respect to x, 2 and -1. So we have 4, +2, -3, -1, +2, right? Okay, can you please calculate? This is 13. Very good. Okay, let's do the partial derivative with respect to y. So we have f partial derivative with respect to y, x naught, y naught. Okay, let's take a look. We treat x as constant, right? So 0 for the first term and second term. X is constant, so negative 3x, right? And partial derivative with respect to y, so we have 16y. And x is a constant, 0. And derivative with respect to y, negative 4. And we are constant, which is 0, right? Okay. Let's evaluate when x naught, y naught equal to 2 and 1, negative 1. So we have 2, negative 1. So negative 3, x equal to 2, plus 16, y equal to negative 1, and minus 4. Can you please calculate? Negative 26. Excellent. Okay, how about this? We need to evaluate. So let us do this one. So we have f of 2 and negative 1. So we substitute x equal to 2, y equal to negative 1, right? So 2 squared minus 3 x 2 y equal to negative 1, right? And plus 8 y squared negative 1 squared plus 2x 2 minus 4y negative 1 plus 4. Whew. Okay, so I don't make a mistake, right? So let me double check. Okay, so what do you get? We get 34. Very good. Okay, so all together, one more time. Let me just bring here. Okay, so that will be z equal to, we have partial derivative with respect to x when x naught equal to 2, negative 1, 13, right? So we have a 13. X minus x naught equal to 2 plus partial derivative with respect to y when x naught equal to 2, y naught equal to negative 1, we get the negative 26. So we have a negative 26. And then y minus y now, which is negative 1, plus, we evaluate the function, we have 34, right? Okay, let's simplify. So we have distribute 13x minus 26, distribute. So we have negative 26, y plus negative 26, yeah? Plus 34. Okay, then that will be z equal to 13x minus 26y minus calculate negative 36, I'm sorry, negative 26, negative 26 plus 34, negative 18. Yeah. Okay, very good. This is the equation, all right? Okay, so here is the plane. We have also tangent plane. So we call this as a surface, right? So this is a surface. And then we have a point, right? So we have one more point. So basically x naught, y naught, z naught, right? So how we get the z naught? We just substitute 2 and -1. Then we get the 34, right? So that is z equal to 13 times 2 minus 26 -1 plus 34 with, oh no, minus 18 equal to 34, right? -18. So equal to 34. Yeah, that's what we get. This is x naught, y naught, z naught. Because they're using x naught, y naught, so I am using z naught. All right. Okay, let's do another problem here. Okay, so here is the question. Find the equation of tangent plane to the surface by the function. Okay. All right. So same processing. We need the equation, right? So partial derivative with respect to x, and we have the point, right? So substitute the point and partial derivative with respect to y, and then substitute the point, right? And then we do evaluation at the point, right? Okay, so we have partial derivative with respect to x first. Okay, so x is here. So what's the derivative of sine? It's cosine 2x, right? And then we make a chain rule. So what's the derivative inside? Then we get the 2, right? Make sense? So you may write down. So note derivative of 2 sine 2x, which is cosine 2x, and derivative of a chain rule. So 2 cosine 2x. Yeah. Okay. So let's write down 2 cosine 2x. Look, this is constant, so we just writing cosine 3y, right? So cosine 3y. Now we want to evaluate. This is x naught, y naught. All right, so f derivative with respect to x, and pi over 3, pi over 4, 2 cosine 2 pi over 3, right? And cosine 3 pi over 4. Okay, so what do you get this one? Cosine 2 pi over 3, 2 pi over 3, quadrant 2, so negative 1/2. So we have 2, -1/2. And cosine 3 pi over 4, also quadrant 2, so negative square root of 2 over 2, right? Okay, then simplify. So we have a square root of 2 over 2, right? Okay, now we do partial derivative with respect to y. So x is constant, so we keep that. Sine 2x. What's the derivative of cosine 3y? It's negative sine 3y. And then chain rule. So we have a 3. So negative 3 cosine. You want me to write down? Okay. Cosine 3y derivative. So negative sine 3y and chain rule. So we have a 3. So negative 3 sine 3y, right? Okay, now sine 2x and negative. Put the negative in front. 3. Ooh. We should put the 3 in front too, right? Sine 3y. Okay, let me put the constant 3 in front. So we will get negative 3 sine 2x sine 3y, right? Okay, let us reevaluate when x naught, y naught, right? So that would be pi over 3 and pi over 4. So negative 3 sine 2 pi over 3 and sine 3y, y equal to pi over 4. Okay, so we have negative 3 sine 2 pi over 3, which is square root of 3 over 2. And then sine 3 pi over 4, which is square root of 2 over 2, right? So simplify. We cannot simplify. Oh, cannot see. Sorry about that. So we can just multiply. Oh, yeah. So negative 3 and square root of 6 over 4. Okay. So let's say using this one. Copy. We can just do that without that, right? We can take a look because I need the space. Z equal to partial derivative with respect to x when x naught, y naught equal to this. So we have square root of 2 over 2. And then x minus x naught, which is pi over 3, right? And plus partial derivative with respect to y when x naught, y naught. So we have negative 3 square root of 6 over 4, right? Okay. Now, y minus y naught, y minus y naught, which is pi over 4. Oh, we did not evaluate. Hey. Sorry about that. So let's evaluate. We need more space. Okay, let's evaluate. So f of pi over 3 and pi over 4. So the function sine 2 pi over 3 and cosine 3 pi over 4. Okay, so what do you get? 2 pi over 3 is the same as previous, right? So we have this one will be square root of 3 over 2 cosine 3 pi over 4 negative, right? Negative square root of 2 over 2. Okay, then we have negative square root of 6 over 4 then. Yeah? Okay. Okay, move on here. Then we do evaluate the function negative square root of 6 over 4, right? We can just leave it like that, or we can make a little bit more distribute, but it does not help. Okay, so let's do the square root of 2 over 2x minus square root of 2 pi over 6 minus distribute 3 square root of 6y over 4. Let's put the y here. And we have a minus and 3 square root of 6 pi over 16 minus square root of 6 over 4. Okay, so if we arrange x, y, so square root of 2 over 2x, negative 3 square root of 6 over 4y, and constant term. Yeah, just leave it like this. Or you can make a decimal. It's up to you. Yeah. Okay. Is it okay? All right, let's move on. Linear approximation. Okay, so here is a linear approximation. What we learned from Calculus 1. It's the same concept, but we are using different equation because we are learning Calculus 3, which is more variable we have, right? So how did we do linear approximation? So what is a linear approximation? So when we want to estimate the value of a function near a given point, we are using the function's tangent line, right? So basically, linear approximation in other book also indicate just tangent line, tangent or tangent approximation, right? So we have in algebra, what's the equation? So we have equation of that, right? Oops. Then pre-calculus, we are using function notation, right? Okay, then calculus 1, we are following same, but then slope, we change that advanced notation, which is slope tangent line, right? Which is derivative, right? Okay, then we make everything one side. So we get that, right? Then that is the equation of linear approximation, right? Make sense? That's why you are here, right? You passed the calculus 1. So this is what we learned, calculus 1. So calculus 3 is the same concept, but as we learned, we cannot make a slope derivative only one variable, right? Because there is more variables, right? So how do we indicate the slope then? Very good. Yes, partial derivative respect to x, partial derivative respect to y. This is what we did earlier for the tangent line, no, tangent plane equation too, right? So slope, right? Okay, so let's take a look. We are using same L. That's the first letter from the linear approximation. But we have more than one variable, right? So we are using xy. Then slope, how do we express partial derivative with respect to x at the point? And then we are using same, right? Oh, missing y minus y naught, right? So y minus y naught. Yeah. Let me make a little bit. Oh. Oh, we cannot make that. Hold on 1 second. Yeah, missing y minus y naught. So let me write down plus with the partial derivative with respect to y, x naught, y naught, y minus y naught, and then function, right? So that is plus f of x naught, y naught. Oh, this is the same equation of the tangent plane earlier, right? Okay. So let's do that example here. Oh, there we go. Here's a picture too, yeah? Tangent plane. So we want to estimate at the point, right? Okay, now, we have the function. We want to approximate 2.1, 2.9. Yeah. And then using 0.23 for x naught, y naught. And then what is approximate value of f of 2.1, 2.9. All right? Okay, so let's find the partial derivative with respect to x. X naught, y naught. So x naught, y naught. Okay, so I mentioned that think the square root, we can use power of 1/2, yeah. All right, so we want the derivative, then we drop the power, so 1/2, right? So 1/2. Then we have 41 minus 4x squared minus y squared, and reduced by 1, which is negative 1/2, right? Okay, now we need the channel, so respect x, right? So chain partial derivative with respect to x, 41 minus 4x squared minus y squared. Okay, so we have 41 minus 4x squared minus y squared, 1/2 power in the denominator. Okay, partial derivative with respect to x. So this is 0, right? 0 minus partial derivative with respect to x, negative x, 8x, and minus 0, right? Okay, we can simplify 4. So we have negative 4x over square root of 41 minus 4x squared minus y squared, right? Okay, let's substitute when x naught, y naught equal to 2, 3, right? So we have f partial derivative with respect to x, and then 2, 3 equal to negative 4, positive 2, positive 2 over square root 41 minus 4x squared 2 squared minus y squared, which is 3 squared, right? Can you please calculate? Oh, cannot see, sorry. -2, very good. Okay, now let's do partial derivative with respect to y. So let's say using same, right? So this is the same. Let me use this. Okay. So we are using y, partial derivative with respect to y. Okay, so that will be 2 square root of 41 minus 4x squared minus y squared. And, ooh, y, right? Y. We want to make a partial derivative with respect to y. So this is 0, and -2y, right? So 0 minus 0 minus 2y. Yeah. Okay, simplify. So we get -y then, -y over and square root of 41 minus 4x squared minus y squared, right? Okay, now substitute. So partial derivative with respect to y when x not equal to 2, y not equal to 3, equal to -3, right? Over square root 41 minus 4 x squared 2 squared minus 3 squared. Can you please calculate? Minus 3 squared. Oh my gosh. Yeah. Very sorry all the time. Oh, you cannot see that. So what do you have? -3 or 4? Good. Okay, so we have a partial derivative with respect to x. And then we substitute x naught, y naught. And we have a partial derivative with respect to y. And then we substitute x naught, y naught. And we have to do function evaluation, right? When x naught, y naught equal to 2, 3, right? So let's see. What's the function? The function is that okay. All right, so when x naught, y naught equal to 2, 3, right? So we have f of x naught, y naught equal to f of 2, 3 equal to square root of 41 minus 4x squared 2 squared minus y squared, which is 3 squared, right? Okay, so what do you get this one? which is 4. Very good. Okay, so linear approximation, what we did earlier, the equation of a tangent line is the same, right? So it's just using the linear approximation. So we have f of partial derivative with respect to x. Y naught x minus x naught, partial derivative with respect to y, x naught, y naught, y minus y naught, and then plus the function value, right? Evaluation. Okay, so that will be let's see. Partial derivative with respect to x, when x naught, y naught, we have -2. So that will be -2, x minus x naught equal to -2. I mean the 2. And partial derivative with respect to y, when x naught, y naught, we have a -3 over 4. And y minus y naught, which is a 3, right? Okay, so we evaluate when x naught, y naught, so we get the 4. Okay, let's distribute. So we have a -2x plus 4, -3, 4y plus 904 plus 4. Let's arrange. So there will be -2x minus 3, 4y. Oh, we get plus common denominator. So 4, 16 plus 9 plus 4. There will be 24, no, 20, 25. Let's calculate. Oh, it's 16, not the 4. Yeah, this one, 32, no, 41, 16. So we get -2x minus 3 over 4y plus 41 plus 4. Yeah. Okay, we're not done yet. We want to estimate, right? So this is linear approximation, which is a straight line, also which is tangent line, right? Okay. Aha, we don't call the tangent line. We call the tangent plane, right? That's why same as equation of a tangent plane. Yeah. Okay. Now, let's see. We want to estimate what is approximate value when x equal to 2.1 and 2.9, right? And then we want to make 4 decimal places, right? Okay, 2.1, 2.9. So let's do 2.1 and 2. Different color. 2.1, 2.9 equal to -2, 2.1, 2.1, 2.1 minus 3 over 4 y, which is 2.9 plus 41 over 4, right? Can you please calculate? We need a 4 decimal places. They say that, right? Yeah, 4. Okay, so we get this one is 3.875. Okay, let's compare original functions. So we can see that here, right? So the original function, how much difference between linear approximation, right? So we always do that. So we have that. So f of 2.1, 2.9, then square root of 41 minus 4 x squared, 2.1 squared minus y squared, which is 2.9 squared. Can you please calculate? So this is approximate 3.8665, right? So we compare two numbers. It's not much difference between them, right? Okay. You guys okay with this? Okay, so we just learned about the linear approximation, which is we want to approximate the function value that given point, right? All right, now we gonna learn differentials. So same as calculus 1, we learned that when we talk about the linear approximation, we always talk about the differentials as well. Okay, let me write down first differentials. Okay, so we have a differentials. So differentials are used in error estimation. So differentials describes small change in the function with input. So dx will be small input and dy we are using small output. So in calculus 1, we started from the equation y equal to, and then function notation. So y equal to f of x. We want the derivative. Then left side, we had dy over dx. And then right side, we have f prime of x. That is the same as Leibniz notation, right? Okay, then we start for dy. Then we have f prime of x dx. We call this as a differentials because we are using dy and dx, which is, I just explained to you, the dy is output small change in output, right? So dx is a small change in input, right? Okay, so dy approximate change in y and delta y, right? So we are using actual change in y. So we have delta y equal to f of a plus dx. We just talked the differential earlier, right? Minus f of a. This is basically calculus 1. So we want to talk about the only this one, propagated error. What's the propagated error? It's a measurement error. So when you measure, there is a small error, right? So this is from the calculus 1. So calculus 3, what we will do, we have equation notation z, right? And this is a function notation. So we are using dx, which is differentials, and then delta x, which is change in y. We know that, right? And we have dy approximate the same as delta y. So what is the dz in calculus 3, right? And we called total differentials. Okay, then how do you make a dz? So we had dy equal to f prime of x dx in calculus 1, right? Then we follow the same concept, but we cannot just do derivative respect to x, right? Because we have a more than x variable. So we do partial derivative with respect to x, partial derivative with respect to y, right? So same, right? This is the same. Okay, so if we are using approximation, then we are using dz, which is total differentials. What about delta z? Delta z is following this equation like a delta y, right? So f of a plus dx minus f of a. Okay, so delta z equal to f of x plus delta x and y plus delta y minus f of xy. Okay? All right, let's do this one. Find the differential dz of the function and use it to approximate delta z at point x naught, y naught, which is 2 and -3. Use delta x equal to 0.1, delta y equal to -0.05. And then what is the exact value of delta z? Okay, so this is the last question. Yay, almost done. Okay, so, let's do it. We want to, why this one? We want to find the differential first, dz, right? Okay, hold on 1 second. Okay, so I erase everything. Okay, so let's do this one. Let's find the total difference first. Dz equal to that. Let me bring the formula here. Copy. Okay, so can you please think about what's the partial derivative with respect to x? This is the last question. So f of, yeah. Okay, so that would be partial derivative with respect to x. Looking at this one, 6x and minus y is constant, so -2x. I'm sorry, -2y and y is 0, right? All right. Then let's okay, let me arrange it this way. So let's make it this way first. Yeah. And then we need to substitute x naught, which is 2, y naught, which is -3, right? So we have a 6, 2, minus 2, y equal to -3, right? Can you please calculate? Which is 18? Good. Okay, how about partial derivative with respect to y? X naught, y naught, which is 0, -2x, and 2y, right? -2x plus 2y. And then we want to substitute x naught, y naught, which is 2, -3, -2, +2, plus 2, -3, which is -10. Thank you. Okay, now we have a dx. dx equal to what? Yeah, so let's make a ID note, right? So they say that, look, dx approximately same as delta x, right? So dy approximately same as delta y, right? So we have a dx equal to delta x, which is 0.1, right? So note dx same as delta x, which is 0.1. So we are using here, and dy approximate to same as delta y, which is negative 0.05. We are using here. Yeah. Okay, let's do it. So dz equal to partial derivative with respect to x when x naught y naught equal to 2 and negative 3, which is a positive 18. And then dy, which is 0.1, right? 0.1. And plus partial derivative with respect to y when x naught y naught equal to 2 and negative 3, which is negative 10. And dy will be negative 0.05, right? Okay. Can you please calculate? So that will be 2.3. Okay. So this is total differentials, 2.3. Okay. Now we want to find, so we found the total differentials, dz. Now we want to find exact value of delta z. So delta z, we need to use this formula, actual change, okay? That's the approximate, right? So this is actual change, so that we can compare. All right, done. This is the last one. We are using 2, negative 3 as x and y. Yeah. So use x, y equal to 2, negative 3, which we used to use x naught, y naught, right? And then we are using delta x as 0.1 and delta y equal to negative 0.05, right? Okay, so delta z equal to f of x equal to 2 minus, plus delta x 0.1 and y plus negative 3 plus delta y, which is negative 0.05 minus f of 2 and negative 3. Yeah, let's just substitute, evaluate, right? So there is f of 2.1 and negative 3.05 minus f of 2, negative 3, right? Okay, the function, we have the function f of xy equal to that. Oh, almost done. Please be patient. Oh, I don't have patience. Copy. All right. Okay, so we want to substitute 2.1 into the x. That means we want to substitute the negative 3.05 into the y, right? Because f of x, y, right? Two variable. So once again, this one to the x variable, and then -3 to the y, right? Okay, let's do that. All right, so delta z equal to 3, 2.1, 2.1 squared minus 2, 2.1, y -3.05 plus -3.05 squared minus f of 2, -3. So 3, 2 squared minus 2, 2, and y, which is -3 plus -3 squared. Can you please calculate? We're done, all right? Okay, so that will be from my previous note, 35.3425 minus 33 plus 2.3425, okay? All right, thank you for watching. I will see you in the next lecture. Thank you, bye.